continuing on liquid-dominated systems, as that example problem demonstrated, a flash liquid geothermal system has a low, what they would call well bottom efficiency, since so much energy is rejected back into the site, especially when it comes to the brine. A proposed solution to that is what they would call the total flow concept for liquid-dominated systems. And that was in which the turbine is replaced by a mixed flow expander that extracts energy from the liquid or from the vapor liquid mixture, thus permitting the total well head flow to be expanded to the condenser pressure. Here's an example of that type of system. Instead of undergoing, again, the flash process, the fluid enters directly from the supply well to a mixed flow expander. And then it comes out of state 3, goes through a condenser process, and then that whole brine solution is rejected back to the ground. So again, you have here state 1, some saturated liquid coming in. By the time it gets to the expander, you're at a saturated liquid vapor mixture, and it goes through the expansion process at that point. Okay, so let's go ahead and try an example problem for this. The example problem reads, consider a total flow geothermal system using the same well bottom conditions as example 13.2. The fluid enters the expander as a saturated liquid and is discharged at 10 kilopascals. Determine the thermal efficiency, the heat rate, and the flow rate for a 10 megawatt system if the mixed flow expander possesses an isotropic efficiency of 50%. So we're saying assume a saturated liquid. So in this case, in the prior example problem, it's saying that the water was at a well bottom temperature of 225 degrees and a pressure of 8 megapascals. So if we were to assume that when we hit state 2, right, when we hit state 2 here, just going into the mixed flow expander, that the temperature is still 225 degrees. That would give us a saturation pressure. Again, this is for a quality of 0. That would give us a saturation pressure of 2.55 megapascals. So in that case, we have saturated liquid as stated. So we have here our enthalpy and entropy of a saturated fluid entering the mixed flow expander. Then coming out of state 3, at least the isotropic version, the pressure is 10 kilopascals. Entropy at state 3 is equal to state 2. You get here the enthalpy coming out for the isotropic version is 802.6 kilojoules per kilogram. And that would give us an isotropic work of 164.2 kilojoules per kilogram, which would give us an actual work of 82.1 kilojoules per kilogram, which I'm just going to go ahead and compute the mass flow rate needed for this. So we have the 10 megawatts worth of required energy divided by the 82.1 kilojoules per kilogram worth of specific work. So we need 121.8 kilograms per second. This is the main thing I wanted to look at in this problem. I know it's asking us to compute a lot of other things. We'll go ahead and compute the efficiency as well, but I wanted to make sure that we focus in on the difference in flow rate. Here we need a flow rate of 121.8 kilograms per second, which is much lower than the 200 plus kilograms per second worth of mass flow rate we needed for the other example problem. So again, it's the same supply conditions, just two different types of geothermal configurations. And this one requires less mass flow rate than the other. And if you were to go ahead and compute the efficiency, again, which would be the actual work over the change of enthalpy in and out of this of the ground, in this case, we would end up with 9%. So the efficiency is not over 9% instead of 5%, which requires a less mass flow rate as compared to the other system for the same well bottom conditions to get the same amount of power, again, being 10 megawatts. There are other systems as well. Again, we looked at the fact that there are binary geothermal systems. So in a binary geothermal systems, two fluids are involved. You got the hot brine from the geothermal well and a working fluid, generally a hydrocarbon, that circulates in the closed portion of the system containing the turbine, condenser, and heat exchanger. So in these binary systems, the hot brine for the well supplies the hot fluid and the heat exchanger in which the organic fluid undergoes evaporation. The organic vapor is expanded through the turbine and condensed in the condenser, and hence is in a closed system. The cooling tower is used as the cold medium in the condenser. The working fluids in these binary geothermal systems include propane, isobutane, isopentane, and water ammonia. Here's an example of that binary liquid-dominated geothermal system. So again, you have a heat exchanger that basically takes in the supply water from the ground, and that water goes through the heat exchanger, gets re-injected in order to be able to evaporate a working fluid. That working fluid goes into a turbine, goes through a condenser, and in the condenser comes out as a saturated liquid going to the condensate pump. And then it's condensed. The organic fluid is condensed by exchanging heat with a water that circulates through the cooling tower. This photo is a geyser geothermal hydrothermal power plant. So as you can see, you have this geothermal plant planted using the hot resource from a geyser. Here's an example picture of the Mammoth Pacific 1, which is a binary geothermal power plant, as well as what we would call a double flash geothermal power plant called Navy 1.